clouds and boundary layer. So that results actually I will just present here as a kind of overview of the work which is being reported. This is
Sanjay, you can make it full screen.
I should wait?
Yeah.
Yes.
Yeah, you can proceed.
Okay, thank you. Thank you very much. So as we for the any of the scientific work, first we observe, then we try to measure it, and then analyze and predict and or model it. So what basically is that we can see with naked eye many of the phenomena, but our eye is not sensitive to capture the very fine mode of where the sensitivity is not there. So to utilize the eye to see that, suppose for example, we can take a laser or this lidar, we can take as it is observing that the atmosphere. For example, in a given day, typical day, we can see this type of the atmosphere, right? Isn't it? So then what we see, basically if you see up, then we see the clouds, and sometimes when we have the hazy atmosphere, we can experience of the aerosol also, okay? And variety of clouds will be seen. And you know that every day is not the same way. Maybe some days rainy, some days cloudy, some days clear sky. So we have different types of weather and all these things. So curiosity may come to us that how to, although we see how to measure it, how to profile it. So then development was there, and then we have there are various instruments, remote sensing instrument. One of that of the lidar. So lidar can be useful to understand the atmospheric boundary layer variability. That also we don't see, but we experience, we study then, and aerosol also, right? And the cloud we see basically, okay, we see the cloud. So, but how to measure it? So lidar, which sends the laser to the atmosphere, give the backscatter coefficient, and that will give the information about these parameters. So we are located here in southern peninsula, this near to the Bay of Bengal, and you can see that map, Indian map we have shown here where our laboratory is located, and I have shown here the topography, how it is our near to location. So we have very smaller hills. You can see about less than 150 to 200 meter, and we are located here about 48 meter from the sea level. This is the black dot. Also, we have very near to that, we have looked with this IMD, India Meteorological Department, Chennai, from where the radios and other meteorological observations are there. And we have this container where this lidar is actually kept, and from this actually we operate this lidar, and the lidar is here, Micro Pulse Lidar. So we take the observation of this location. So this is the specification, technical specification. We have that we fired the laser with the 530 nanometer, and the energy actually will be not constant, is varying between 3 to 4 microjoule, and with pulse repetition rate the 2500 kilohertz. So sorry, 2500 hertz, and pulse width is less than the 10 nanosecond. Maybe all these things I think about lidar. You have several talk by the many experts, so I may not go much detail, but I say about here the technical specification, what we have the system. So we have the receiver for this the MPL, the Galilean telescope we use, and diameter we have 80 millimeter, and field of view 200 microrad. So then how this lidar works? So then we actually transmit the laser, and then again I say that already you have gone through this the principle of lidar, so I need not spend. So here the instant the energy will receive, so that's what we have, and then the energy transmitted and the function of the backscatter coefficient and attenuated coefficient. So that's what we have here, and from this one we basically get normalized backscatter backscatter signal. So then we have to wait because that depends on the how much energy will be fluctuating, so that we have to normalize with that one. And also the overlap factor we have to get it, because I will just come to that one. We have when you have this system, you should actually in hand you have to correct some of the or the calibrate that your Micro Pulse Lidar. And the challenging issue is that to get this overlap corrected profile, and as well as you need to also, when you are driving that the backscatter coefficient, you need to know about the lidar ratio. So here how we do that for getting this lidar the overlap factor, we have to operate that lidar in the horizontal direction, and you should understand that the assuming that the atmosphere is homogeneous, so then we can get that the overlap factor. So how it is actually is that one, because you see that there is a transmitter and receiver T and R we have placed. They see that there is a not, though it is a biaxial, it is not the together. So there will be transmitter and then receiver, then there will be not overlapping. So for some region, for us it is 260 meter. It is, this will be not overlapping, so we will not get any signal. So this is the blind region, and there will be partially overlap for about, we have about this the 1.1 kilometer here to 0.9 kilometer for some typical case, and then above it is no problem. So then we have to correct this, and so that we find it and then fit it and then get the overlap factor, and then we correct the signal. Also, another thing is that how to fix this when we are driving that one important thing is that to fix the reference altitude and also get the lidar ratio. So to get this because the signal is not the same every day and every time, depending on the weather or the atmosphere. Okay, so during night time we get the signal about the 14 to 15 kilometer, but during daytime it is the 5 to 6 kilometer only. So now to fix that, how to get that the backscattering and extinction coefficient derived. So for this, first of all, we get the reference altitude by do that we do actually we calculate this signal to noise ratio by taking the mean, and then we are finding that whether it is the more than one standard deviation the signal, then we tell that okay, signal is there up to that altitude. So, and then finally when we calculate the lidar ratio, for lidar ratio we had actually here some the macro top sun photometer. So then we have also observed we operated together and we apply this iterative method. So then we can actually get that the lidar ratio for a given profile or given day. So what we do that we start with the 20 lidar ratio, assuming that 20 to 70 or something, that 20 to 100 actually the lidar ratio varies over this location. So 20 to 70 we just start from the 20, and then we increase with one lidar ratio and then do the iteration, and when the observed AOD with the AOD calculated from the iteration is converged, then we take that lidar ratio, corresponding lidar ratio for the rest of the derivation. So these two problems will be there when we are operating the lidar at a new place. So this is the profile we have obtained, the extinction coefficient. So it is shown here, or this is from the 15 IST during daytime, and then during night time you can see that 10 to 12 kilometer we can get this extinction coefficient, and then morning also again it is decreased. So like that we have the extinction coefficient derived. Now once we have the profile in the hand, then we can study the first. The interesting thing comes that the atmospheric boundary layer. So then you might have seen also the what is the importance of atmospheric boundary layer. I may not go to that one. So just I will come to the sum of the observation. So I show here first, because we are located at the coastal station, I show one schematic diagram over the land. This is taken from the NARL Gadanki, where I have worked on that one paper there. So it is shown here how this diurnal variability of ABL during the winter season and during the summer season is there. So you can see that the diurnal variability of the ABL, during the morning time, okay, this will be the stable boundary layer, and then during daytime it will be the convective boundary layer, and then again nighttime stable boundary layer. But along with that, there will be the residual layer during nighttime, and you have this entrainment zone and capping inversion, that one. So what is happening here during the winter time? We see that there is a we have this the mean plot I have shown here, that you see that there is a always we have that kind of the inversion layer over that, and that is not varying the much with time. It will be that is what. And during the summer season, we have this the strong variability with the day, within day. So the convective boundary layer, you see here, the little bit higher during the summer season, and the so over the land we have nice this diurnal variability, but during winter and summer there is a difference between these two variation. Now coming to the coastal region, beside this the formation of the convective boundary layer over the land, we have the internal boundary layer here. So how it is actually because of the sea breeze onset over the coastal region. So as you know that how the sea breeze onset is there, because we are located in coastal station. So what happened that the heat capacity of the sea is high. So what happened that it will be cooling the less faster or the than the land. So what happened that will be the sea will be cooler and the land will be warmer. So then there will be the differential heating, and then there will be sea breeze circulation. Now near to this coast, if you are there, then you will experience the high wind, the strong sea breeze, and as you go, it will be you may experience less sea breeze, and it is actually faded away as you go from the sea coast about the 50 to 100 kilometers. Next is that when you have this sea breeze, there will be the internal boundary layer will be varying with the fetch. So near this sea breeze, the fetch, the internal boundary will be lesser height, and as you go away, it will be growing. So that the internal boundary layer grow with the fetch. So that whenever the onset is there, the CBL will be disturbed. So there is an internal boundary layer will be formation will be there. So generally over this station, what we see that most of the time you see the double mixed kind of the layer over this station. One is the TIBL, then there will be CBL, and during night time also it persists most of the time the residual layer. So then mostly it appears that daytime and night time, or the morning time and the evening time profiles look similar, same. So you have always the double kind of the layer. So how to calculate this sea breeze? So what we do that we actually we should have that for the surface observation. So then we should know that whether this we have to calculate the sea breeze component and the coastal breeze component. So sea breeze component you can calculate, but that I have shown here. So surface wind we have, then we will calculate that one. And the sea breeze component, once you calculate, then you will know that when the sea breeze onset is happening. So once the sea breeze onset is there, then you will see that there is a modification in the coastal modification in the convective boundary layer. So here you can come here to the lidar observation. You can see that one typical example which I shown here. If it is no sea breeze, then you can see that the ABL grow like this. I think my pointer may be there, I don't know. So ABL will be growing, and then you have the the convective boundary layer. But what happened? You can see in between is a flow of the sea breeze. So what happened that there is a disturbed, and then the TIBL below and the CBL above, and night time we have. So this is again you have the SBL. Okay, always we not able to get the SBL, but yeah, during winter season we get that because it will be deeper during the winter season. So generally we get that. So then we see that there is a yeah. So then you can see that there is a modification in CBL. Similar way, different season also we have. this C bridge, and then there is a modification in CBL, and then the internal formation of internal boundary layer. Here we have shown the occurrence. So the occurrence, because we have taken the observation at Binambakam, means that near the IMD station and also our location. We are actually about 12 kilometer aerial distance apart from that one. So we have to compare also. So little bit we see with the fetch. Little bit we see that with fetch that we have this ABL will be higher over Katankulathur, TIBL will be higher over Katankulathur over this station, and from the Minambakam, from the near the coast. So that what here we have also shown that thing, that TIBL over this Minambakam station, and then TIBL over this Katankulathur station, so with higher, and then we have shown here the distributions with season. Now I saw the typical case for the diurnal evolution during different season. Already we seen there some of the typical example. Again, I saw that here. So during winter season, we have the ABL is low at lower height, means the depth of the ABL is lower, and during the summer season it is higher. So we have shown here the different types, considering that during during this winter we have the more stable condition kind of thing, and during that see that here the pre-monsoon season we saw March, April, May. So then that time actually there will be the kind of the EAL formation or the elevated aerosol formation, and then there is also the frequent occurrence of TIBL, and then very lots of structures are there in the atmospheric boundary layer. And during the summer monsoon season, when convection is very strong, what we see that the disturbed ABL height, it is very difficult to find the ABL height during that time. You can see that we have this SBL, and then it is the SBL. Then there is a very difficult to find this the CBL height. So then you have the clot of boundary layer also. This kind of the clot occur at the boundary layer, and the temperature profile. What we have shown here, the potential temperature profile, you see that it's different. So because of this convective forcing that takes that so much entrainment, and then there is a kind of the different the mixing and all these things, strong mixing, so leads to the different temperature structure. And then finally the post-monsoon season or northeast monsoon season is similar to the winter season. So we have very low ABL height. Of course, we see the formation of this. There will be the TIBL formation also, but not frequently during this post-monsoon season. So here we have made the statistics. So we have the total observation, and then we have that how many times of the observation of the TIBL and the frequency of occurrence. And we have shown that how they are actually the mean, the ABL height and residual height, and also the pink color what we shown here is the TIBL when it is occurring the mean height. So we see that all the seasons the ABL variability over Katankulathur. Then also we compare just to know about the forcing. So generally it is the surface forcing. We take temperature, and there are many other forcings also there. But first we have just see that how this diurnal variability of ABL height and the surface temperature is there, and also the peak timing, peak temperature and the peak ABL height. We were checking here, or we are showing here that. So it is similar. So what is happening that ABL height also become higher when the surface temperature is more. But generally there will be the 2 hours or 1 hour difference in the peak temperature and the peak ABL height. Then this observation we had in our hand. Then because when we are actually studying the TIBL over this station, so we have the 2 observations. One is the Minambakam, one is the place where Katankulathur. Now to understand that how the ABL vary with phase, we don't have any observation in between. So what to do? So then we have to rely on the model. So for the model, if you want to do that one, first we have to know that whether the model is working fine or which scheme is suitable for this location. So what we have used that we use WRF model, weather forecasting model, and we use 5 different scheme for that, generally used for the tropical station. So we have used this asymmetrical convective model, SEM2, onset university model, YCU, and AMDA genic model, that scheme, MYJ, and Miller AMDA, Nakanishi, and Nino level 2.5 MYNN2, and also the Begol Bullock scheme we have also. So 5 schemes we have used here to test that the observed ABL height and the simulated ABL height, how it is actually working. So then here is the specification. I will not go to detail in that one. You can go to the paper, already it is cited here. So, and then what we did that we have taken 4 typical cases. Typical cases already we have seen earlier. 4 typical cases we have shown here of the ABL variability during the taken different seasons. So we taken winter, a typical case, pre-monsoon, post-monsoon, during monsoon, and post-monsoon. So then we identify the ABL height here, which is shown, and then also we compare. And then simulated ABL height and observed ABL height we are showing here. Also, we have taken 2 observations, 1730 and 530 IST at IMD also. So then we are comparing. So you can see that all more or less ABL height simulated one and the observed one is the more or less comparing. But what we see that out of them, MYNN2 scheme actually compare better than the other scheme. During daytime, all the models more or less comparing, but during night time, the MYNN2 scheme is comparing better than that. So we prefer that over this location. We can simulate that boundary layer using the MYNN2 scheme. And also we also simulated the surface temperature and relative humidity. So more or less all the schemes are fine with some description that this better performance we are getting from the ACM2 and MYJ scheme. So that from the boundary layer and surface the parameter, the schemes are actually differing in the simulating that one. So sorry. Then also we have simulated the vertical profile of the potential temperature, and we see that the better the schemes what actually simulate that we have that is MYJ and MYN2 scheme. So out of 5, these 2 schemes actually perform better in simulating the potential temperature. So like that we have used that boundary layer data to characterize that atmospheric boundary layer and also the simulate that one. More work has to be done using this data. So next we observe this tropospheric aerosol. So when we started the experiment, then we had the observation in our hand. Then we thought that when we should have one more observation to see that how is it actually when we are observing the first time. So then Calypso was the one that passes near to our location about 90 kilometer and 70 kilometer to that day-night passes. So we had that one data, and then we thought that why not we should see that how the Calypso performs with the ground-based observation. This is not done over the tropical station. The comparison or validation, there were mostly the European stations and the Western station were compared. Though it was compared, the Calypso is operating since 2006, and the validation long back done, but we had the chance to do that again. So we had compare here, and we taken that different sky conditions to compare it. So we collected the data for 3 years, and then we had a clear sky observation and compare that one, also the mid tropospheric cloud condition that we have compared also, and then we taken also cirrus cloud. There were some of the study that during cirrus cloud observation, the comparison of the aerosol profiles is not like that the clear sky profile. So then how these relations we do not confirm that what could be the reason, but there is a larger deviation in the when we have operated the lidar in the presence of cirrus cloud and compare the aerosol profile with the cirrus. So there is a difference between Calypso and the observed from MPL is the larger when compared to the clear sky. So that's what we have observed. So here we have also understand that, because again it is coming to that what lidar ratio you're using, because the Calypso have some technique to have that lidar ratio and then calculate that the profile, and we have some other things. So in order to understand what Calypso gives the lidar ratio and what we have used, so whether due to the lidar ratio some differences are coming, some of the studies were there. So we get some connection, but we cannot just point to lidar ratio only that the difference is coming, because again complexity is coming because of the what type of the atmosphere we have that time, because the difference between the two observation is different. One is 90 kilometer away, one is the 2 or 90 kilometer away. So then we do not know the atmosphere between these two, because that will be also causing the variability in the aerosol profile. But more or less, when the homogeneous condition is there, we observe a good agreement. What I saw here is a good agreement for the CALIOP observation and the MPL observation. So there is a difference. So this difference is actually coming in the range of what is published from the other at other location. So that is comparable to that one. So we have compared both level 1 and level 2, and we have got a very good comparison, and we are sure that the Calypso can be used for our location without any doubt. So that's what we thought, but we have to be cautious about that. We should not use the profile with the bad quality. Then we have also studied that the characteristics of the aerosol. For that, again, I saw the 4 typical example during different season. So here again, the different types of the boundary layer during different season. So one is that during winter season, we don't have the EAL, and in the post-monsoon season, you can see that very nicely the EAL is also there, and there are different structure of the ABL, the stable boundary layer, residual layer, CBL, and all these things here depicted. So with the different types of the aerosol evolutions over this session we can see. Then we have done the mean of that during different seasons. So we can see that the boundary layer, within this during the winter season, we have that almost exponential decrease in that one. But during the pre-monsoon season, what is happening that because of the many times formation of the this EAL, we have that the aerosol aerosol concentration actually up to the higher altitude, about 4 to 5 kilometer is the more occurrence of these aerosols. Similarly, during this summer season, so we have this different aerosol profile, and during post monsoon and similar to the winter season. So what we see that there is a, when we plot it together, when we see that there is a distinct structure between the aerosol profiles. Now, to understand how this ABL play a role in the aerosol distribution, because this is very important to understand that how much aerosols actually get deposited or how much aerosol is actually getting into the free troposphere. That's important for the many of the applications. So here we have seen that during the winter season, this ABL contribute more for the AOD, total AOD, whereas during the monsoon season, that free troposphere contribute more for the total AOD. So that's what we have seen from our observation. Now, as we have shown that the pre-monsoon season frequently occurring the TIBL, this elevated aerosol layer. So then we thought that to characterize that, there are many studies over Gadanki also has been done in many other stations. So we thought to characterize that, but major challenge was that to identify it. So we are identifying some preferred method that we have used the zero differential method, and the paper is under communication. So we also characterize that one and also utilize that the Calypso observation also together with that one whenever it is available to see the longer term the EAL occurrence and the distribution. So here I am just showing the mean. So you can see that clear sky how the profile is there and how this the when the elevator aerosol layers are there. So profiles are this one. And also what is the total observation gone to that it is shown here for the 3 years, and also the from the CALIOP 2007 to 2018 we have shown here. So like that, this study also, I'm not showing the complete result here, but that's what we have done. Now I'll come to the upper part. So
Dr. Sanjay, sorry to interrupt you.
time is over.
You have 5 more minutes for presentation and 5 minutes for discussion.
Okay. Then I will just move a little bit faster. So here I saw the cirrus cloud observation. You see that the cirrus cloud observation, then we identify it, zero differential method, as I said. So the different type of cirrus cloud, one is that the laminar cirrus, and other is the descending cirrus, and then this kind of the wide cirrus, we can say that the very wide cirrus is there, broader cirrus we can say, and then there is a multiple cirrus. So 4 types of the cirrus, and then how to identify. Again, it is a challenging task that how to identify, but zero differential method works very fine to identify it, and we could able to get that base and top of the boundary layer. So this is the observation what we saw here, the total observations of the cirrus cloud and the clear the total observation. Yeah, cirrus and total observation, other observations. Then here it is very nice thing that what we have got. So we plotted, as I said, that the multiple cirrus occurrence are there and single cirrus occurrence are there. So we plotted separately. When we plotted together, there is no diurnal variability was coming. So when we plotted separately, there was a diurnal variability in the cirrus occurrence. So for this, the single cirrus, actually, it is evening time, it is having the maximum occurrence, whereas that for the multiple cirrus, it is the morning time. So then we try to understand what is this cause. So we just have the sum to understand that we don't have the other data set to conclude that. So we thought that whether convection playing role or whether the freeze drying is playing role. So we had the temperature observation during morning time and evening time. So that's what we plotted here, and then we have taken the deep convection, whether it's playing that role. So we have also. So what we see that for the single layer, we see that during the this is timing is the evening time, it's picking up. So of course that we have evening time more. This evening time, yeah. So no, this is here the convection. So convection is playing. So convection, what is happening? That convection we have that during the evening time. So that what actually the mostly is playing for that this one, the formation of single layer. For multiple layer, what we see that the freeze drying mechanism is playing more, because we see that the morning time we have the more the temperature goes less than 191 Kelvin. So what we attribute that it could be the reason that the colder temperature initiate more of the multiple cirrus cloud. So then we have the extension, and then just I want to here indicate that there is a how many times the cirrus cloud actually forms above this tropopause, and that has the roles for the of course the radiative impact on the stratospheric change. So that's what we have here. So then we saw that there is quite a few times it goes to the in the lower stratosphere. So then it has the implication for the radiative impact on the stratospheric compositions. So then also we have looked into the annual variability, different years, and we could not able to understand, because very near to our station is the Gadanki. There the occurrence are showing that during the monsoon season more occurrence of the cirrus cloud. Of course, we also see the same, but the distribution was completely different from one year to other year and the next year. So we thought that how it is coming. Many times we analyzed this data, the results was coming the same. So then this is the distribution. Then we try to understand whether it is because of the internal variability. So we studied this, and then we just saw here the convection is wherever the convection is more, the occurrence was more. That's what we see first thing. That's what we have in the average one. And then when we see with the internal variability, El Nino or the ENSO component and the KIBO component, they are actually very nicely correlating. So what we see that there is a link with the such variability due to the internal component. Now to finally understand the relative impact, I think the time is not much, but what we did that we also important thing that what is the role of this cirrus cloud on the upper tropospheric temperature change or the near the tropospheric temperature change. So first we have to know the occurrence, and then we calculated that one. We find that there is a the cirrus cloud occurring at the tropos actually warm that. So that's what we have seen. So then same work we have repeated here from the MPL observation. So then again we are seeing that there is a effect from the cirrus cloud, and the very nice paper was from one of the Sen et al, and then he has also seen very nicely that the cirrus cloud play a role right on the warming there. So we see that one. So and then we categorized now the different type of cirrus cloud, subvisible cirrus cloud, optically thick, thin cirrus cloud, to understand more clearly that what is the role of these things. So then we are working on this paper, and we will submit that one. So that is what we see, that the different types of them. There is a kind of different pattern we see. The heat warming we see, and when this where cirrus is there, and this warming and cooling, actually what happened with that, the changes changes with the cirrus vertical extent. Yeah. So thank you very much. I think I have so many data shown. So yeah, thank you very much.
Thank you, Sanjay.
Yeah.
I request the online participants and participants present here, if there are any questions, quick 1 or 2 questions. The participants online can unmute themselves and ask the questions. Okay, if there are any no questions, I have a couple of questions for Sanjay.
Please.
The first thing is, so the mini MPL software itself can identify the boundary layer and load it, store it in the text file, right?
Yes.
So did you ever compare the automatically identified boundary layer with your own algorithm identified boundary layer? So is there any difference, or?
No, we store that data, but we have never compared, because our see what happened that it is I don't know what algorithm used, maybe the gradient method or something. So what happened that wherever the gradient is there, small change in the gradient or the power change or something, they detect that one. Okay, so that is not the actual ABL height. But there are times when very good data is there, the software also detect the similar ABL height. But most of the time, as we shown that many of the profiles I have shown you, there are so much changes are there because of the one is the coastal region, other is the weather changes, and then there are many other changes are there. So just directly automatic algorithm is very difficult to get the complete ABL height. So we do not take that data, and we identified using our method.
Okay, that's what my question is. How much bias, if you have compared both these, how much bias you have identified?
No. I did not work for that. No, I did not work for that.
Because I heard they are using sophisticated algorithms to identify the exact boundary layer, what we identify with our own algorithms.
Okay,
so maybe
but,
try
yes. Yeah, then that one work can be done comparing that one, but I don't see any of the paper that related to that their software being used for the identification of ABL height. Rather, they use their suppose that the covariance method or other method, logic method, to identify that one. Till not, I have not got any paper that MPL directly retrieval they have used for the research work. Maybe operational is fine. Operational is fine. You can use that one.
Okay.
Yes.
Okay, thank you. And another question is, what are the operational difficulties you faced when you are operating this MPL at Chennai site?
Yeah, that is very good question actually. This is luckily I am telling that I don't know whether I was sincere or something that was interested too much, but any mistake means that we were very cautious to operate that one, so that the instrument should not go bad, and then we train the student in such way that they should be very careful. So first of all, the sudden rainfall generally it occurs during the evening time, so that's what we have to take care into. we have to be alerted always, because that is that you are work about the lidar, that any small drop of water can cause that optical instrument to go bad.
Yeah, yeah.
So that's what. So that is one caution. Other thing that you of course you for the lidar scientist, everybody knows that you have to how clean you have to keep the atmosphere there. Okay, so of course we have maintained those things. And the challenging, as you know, that we are not in the very well developed research place. We are the educational place. So here, of course, they may not be having that much that much idea for that thing. So anyway, that we try to keep the standard way of operating that one, because yeah. So that was.
So you
that's
keep
what
the skylight open always, or you have any glass window? Just the open skylight.
We have the glass window. We have two closing. One is the sudden close we can do, fast close, so that we had. Other is that lead was there to go up and then close that one. So something is happening and suddenly we are closing with the glass. So that's what we have the.
No, what I am asking is, while operational, means when you are operating the instrument, you are using the skylight, closed skylight, or just the open skylight?
No. Open. We are not having any glass in between that. We do not do.
Okay.
We tried with the quartz plate, but we could not able to successful because of the we do not get the proper quartz plate, and also that to put the proper angle for that thing, it was very difficult to do that one. So we opened the clear sky, means we opened the open sky only, operated open sky only, not having any glass.
Yeah.
And because one other problem is that laser power is very, very less. It is 3 to 4 microjoule. So if you operate with the glass, means it is mostly going to be attenuated here itself. So may not be able to get the good signal to the higher altitude.
Yeah. Moreover, it may be misaligned.
Yes.
Yeah. Okay. Thank you, Sanjay, for your nice talk.
Yeah, thank you, Dr. Rajaman. Thank you very much for giving me opportunity to talk. I could do better, but anyway, next time. Thank you. Thank you very much.
Yeah. Thank you very much. And we are going to break for tea for 10 minutes, and we will meet again at 11:15 shortly.
Okay, thank you very much.
The next presentation will be by Dr. Punaram Sinha, IIST. Hello. Hello.
Yeah, go ahead.
Hello. Hello. Can you hear me? Hello. Hello. Hello.
Yeah, go ahead.
Yeah. Can you hear me?
Yes. Clear.
Yeah. Welcome back. Sorry for slight delay. Now, Dr. Punaram Sinha from IIST, Indian Institute of Space and Technology, Thiruvananthapuram, is available with us to deliver the talk. Now, I request the student to introduce Dr. Punaram Sinha.
Dr. Punaram Sinha, Associate Professor in IIST, Thiruvananthapuram, India. P.R. Sinha obtained his PhD Physics in 2012, working at TIFR Balloon Facility, Hyderabad, and awarded at P.T. Ravishankar Shukla University, Raipur. He was postdoctoral fellow and project assistant professor during 2015 to 2017 at the University of Tokyo, Japan. He joined as faculty at Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram, in January 2016. His primary area of research includes aerosol dynamics, aerosol radiative forcing, aerosol cloud interaction, aerosol boundary layer interactions, and technical teaching includes radiation process in atmosphere and ground and satellite-based measurement techniques and instrumentation for atmospheric science study. He participated in national and international field campaigns over land and ocean. He is authored and co-authored of 35 research papers, peer-reviewed journals in the field of aerosol science. May I now request Dr. Punaram Sinha to proceed his valuable talk?
Yeah, thank you very much for a nice introduction.
Dr.
And
Sinha,
let
you
me
may please
share my
proceed.
screen if you can.
Yeah. We are
Yeah.
ready.
Can you remove your screen so that I can
Yes.
share the screen, please? Yeah.
Where is his screen? இது எடுத்துட்டு அவரோட பிபிடி ஷேர் ஆகும் இல்லையா அவர் ஆல்ரெடி ஷேர் பண்ணிருக்காரு. Dr. Sinha, you already shared your PPT? Yeah. Can you please share your screen? Dr. Sinha? Dr. Sinha, can you please share your screen?
Yeah, I already did, Rama. Could you please take?
It seems some network problem there with you. Yeah. I will share. I will open. Allow me to share. Hello, yeah, I am sharing.
No, I think am I audible and my screen is visible?
No, not it.
Really? So, Dr. Raman, I just now shared my present. Could you please open that one? Yeah.
Now he shared. Yeah, now he's open. Yeah, you can proceed.
Okay. Thank you. So, let me thank Dr. Raman for this opportunity and greetings to entire team of ISI 2022 for this very important workshop dedicated to one single instrument, which is the backbone of this Lidar for aerosol and cloud studies. So my primarily area of research basically includes of Lidar for aerosol studies, and what to give you a brief introduction about aerosols, because in audience, and the audience is of wide spectrum, it is really task to have a very balanced presentation that I have tried, and I hope you will be able to follow up. So I'll give a very brief introduction about aerosols and basically and then motivation that research addressed and the results from that scientific problem, the challenges we faced during IIT, and then recommend